What's up, guys? This is Cerd. Today we're going to be starting to build on an AI. It's going to play video games. It's going to be looking at the screen. It's not going to be cheating or reading the in-game's memory, so there's not going to be any hooks. You'll even be pressing keys just like you would. I'll be building the whole thing by hand. I'm not going to use any PyTorch or no machine learning libraries, nothing like that. I'm even going to be staying away from Python as that's one of my comfort zones. So I'm going to be learning Rust as we do this. And I honestly know very little about Rust, so I'll be learning right alongside you, just from the Rust side of things, I guess. And we'll even be building or doing the math that lets a neural network learn. So before we get started, if you're here for gameplay footage, there's no gameplay footage yet. This is actually just day one of starting the code. Anyone can import a library and train a model. I actually want to build the engine from scratch so we can actually understand what's going on under the hood. So we're actually going to start with the smallest, most fundamental part of the whole thing, and that's actually the part that lets a neural network learn. So what are we actually building first? I'm going to butcher the pronunciation of this because I am terrible at speaking. It's a thing that's called an automatic differentiation engine, or autodiff for short, which is what I will be calling it because I can't speak. I know this sounds like a mouthful, but stick with me because it's basically the heart of how a neural network works. Alright, so here's the deal. When a neural network learns, all it's really doing is tweaking a bunch of numbers to make its mistakes smaller. And for it to tweak each number the right way, you gotta know one thing. If I nudge this number a little, does the error go up or down? And how much is it going up or down by? That how much does it change thing, that's actually a derivative. An autodiff, that's just how the computer figures out all of those derivatives for you on its own. So when we're looking at these derivatives, there's basically three ways you can get them. You can do it by hand with calculus. That's fine for something tiny, not really feasible for networks with, millions of numbers. You can do it numerically, which is where you nudge the input here and you monitor the output. And you just see how much it moves. That works, but it's slow, it's really rough. Or you could do autodiff, which is what the real machine learning libraries do. The computer just watches every step as it runs and works out the exact answer. So the thing with autodiff is it's not actually a giant elaborate formula, and it's not really a guess. It's exact and automatic, and it comes from just keeping track of what's happening or going on, like bookkeeping, for instance. And because we've got millions of inputs and only one output, if we're looking at autodiff going in a forward direction, we actually run into an error. The way we get around this error is we actually run the whole thing backwards. Everything forward first, and then we walk it back to answer every input in one go. That backwards walk's got a name, and you might have heard of it. It's backpropagation. So reverse mode autodiff, which is looking at it going backwards, it's the same thing as backpropagation. So let's slow down here and look at one word or concept real quick because it's kind of really important, kind of a big deal, kind of everything. That word's gradient. So it's a gradient. So the derivative of something at a point is just its slope. How steep is it going up or down where you're standing? So if that's the case, then if the slope's 3, nudging the input by a hair would increase it roughly 3 times as much. So if you think of this like standing on a hill, it's just how steep the ground is under your feet. But realistically, a real network, it's going to have millions of inputs. So the gradient is all those slopes at once. That's going to be one number per input, each one basically going, hey, if you nudge me, here's how the error moves. So picture the error as a big valley, and the gradient points the steepest way up. But that's not the direction we want to go. We want to go down. So we just turn around and go the other way. So if we look at it from this perspective, we're going downhill a little bit at a time, over and over. The error shrinks, and that's it. That's what learning actually is. So the concept is you connect to a game, you work out the gradients, it steps downhill, it does it again. That's why the first things we're going to be doing is we're not connecting to a game or even building the network. We're actually going to be building the thing that works out the gradients. Okay, so now we're actually presented with a problem. And this problem is actually going to force everything we're about to write. It all has to do with a normal number. A normal number, or a clean float, it only knows its value. It doesn't know where it came from or what made it or how it got made. And for us to walk a gradient backwards, every value has to remember its history. It has to remember what it was built from, and it has to remember how to pass a gradient back through those pieces. The plain number can't actually do that. So before we work out a single gradient or move forward, first we have to build a smarter number. So the smarter number is what we call a node. Node isn't just a value, it's a little bundle that remembers four things. It remembers its value or the number that it's holding. It remembers its gradient, how much it affects the final answer, which starts at 0 and gets filled in later. It remembers the nodes that it was built from, or children, and it remembers the function that knows how to pass the gradient back to those children. So let me write that out. That's value data, grad for gradient, children, and this backward field, which is a stored function. And then the things we actually pass around is the value, which is basically a handle to one of these nodes. I'll explain why it's wrapped like this in a second, because this is the first spot where Rust really makes me work for it. So this is something that caught me really off guard, and so this is what my first crack at addition looks like. It looks fine, right? And Rust just shuts it down. You get the error that use of moved value. And here's what that actually means in Rust. So when I pass a value into a function like this, it gets, quote, moved, unquote. The original is just gone after that. So the second I do a dot add parentheses b, I can't use a again. And that's a real problem, because math reuses values constantly. A shows up in a times b and a times c. Addition, or if addition eats its inputs, you can't really build expressions. So Rust is basically telling me these values can't be owned by one operation. They've got to be shared, and this is exactly the kind of thing coming from Python just was not on my radar whatsoever. So how do we fix this issue? So we'll actually be using two tools, I believe. We'll be using Rc and RefCell. For us, a node needs two things at the same time. It's got to be shared because we've got to have a bunch of operations pointing at the same node at the same time. And it's got to be mutable because during the backward pass, the gradient will be changing. Normally, Rust won't let you have both, and it's something intentional. They do it because they believe it'll stop bugs. So we have to reach for the two specific tools we mentioned earlier, Rc and RefCell. So the first one's Rc, or reference counting, and that gives us shared ownership. It's a bunch of handles, one node underneath, then cloning of handles. It's actually cheap. It's actually just another pointer to the same node. It's not a copy, and that's very important, because if we copied a node, we actually split the gradient across the copies, and that would be wrong in the computational side of it. The second one is RefCell. And that actually lets us change the node through a shared handle. It checks the rules at runtime instead of at compile time. So you stick them together, Rc of RefCell, the value data, and now we've got a node that's shared and mutable at the same time. Now I'll wrap that in value so I don't have to stare at this ugly nesting every 5 seconds. Okay, so now for the fun part. Watch what happens when we build addition out the right way. So every time we do an operation, it's going to make a new node. That node writes down which nodes it came from. Do a few of them in a row, then now you've suddenly built a graph. Nodes connected by the operations between them. So say I do A times B plus C. A, B, C are my starting nodes. A times B makes a new node, call it E. And it remembers it came from A and B. Then E plus C makes the answer D. And it remembers it came from E and C. And I didn't build that graph by hand. It wired itself up just from me writing the math. Now the whole tape idea, the graph just recording of what happened in order. And here is the actual trick in reverse mode in 4 or 5 lines. Each operation stores a little function that knows how to push gradients into its inputs. So for addition, the derivative's just 1, so it passes the gradient straight through to both. Inputs, no change, and keep an eye on this. It adds to the input's gradient plus equals. Remember that one? It's going to be the story for what's next episode when we start doing multiplication. So now we need to touch on the chain rule. So we got a graph. Every node knows how to pass its gradient back. And the thing that actually makes it all work is the chain rule. So in one confusing sentence, what the chain rule is if z depends on y and y depends on x, the effect on x on z is just those two effects multiplied together. The less confusing way to remember what it actually is the rates multiply as they chain. So to figure out how some deep input affects the final answer, you multiply the slopes along the path. That's less confusing for me, might be more confusing for you, I don't know. And if the value reaches the answer of more than one path, you add up the contributions, and that's the plus equals again. So what this means is backwards is really just this. Seed the very end with a gradient of 1 is the output effect on itself is 1, and then you walk every node in reverse. As you walk these nodes in reverse, you're calling its stored functions, so each one multiplies the gradient coming in and hands it back. By the time you get to the inputs, every one of them has added up to its total pull on the answer, and the total is bits gradient. One sentence to remember the whole engine theory. Every node knows how to push gradient to whatever it was built from, and backward just runs that for all of them in the right order. All right, are you ready for the moment of truth? Does a gradient actually make it all the way back through a chain? So for A plus B, then plus C. Every input comes back with a gradient of exactly 1, and that's correct. That's what we were actually looking for. So everything here is addition, which means, as we stated earlier, it's passing everything, or passing the gradient straight through. So that stays 1 for the whole way down. My code actually figured that out on its own, and that's a real working autodiff engine by hand in Rust. We did. So this is actually easy mode. This was addition, which is just hands the gradient straight through, no change. Real test is going to be multiplication, where the gradient of one input depends on the other one, and then how do you actually prove the whole thing's right, not just these couple of cases I picked? Well, you have to find that out in the next episode.